Hey guys, welcome to AP level, university level dynamics, so forces and stuff. I just wanted to go over a couple things in the form of a couple of the questions that might throw you. So here we go. First one that might throw you is the first question, so it's fairly apt. Good one to hit. You're basically, you want to find a graph that's going to be like what would be the graph of the net force look like, and you've got a graph of the velocity with time. And the graph of the velocity, this funny symbol means proportional. It's proportional to t squared. Net force is just mass times the acceleration function, and so it'll have the same shape because some positive constant times some function the function will still have the same shape. So if we basically just got to figure out what the graph of the acceleration function would look like, and we can just take the derivative of this. Proportional means just it equals v equals some constant times t squared, and the constant won't change the general shape. So if we take the derivative of it, our new coefficient is the old coefficient times the old exponent, so 2 times 1, there's a secret 1 here. And then we take 1 away from our exponent, so it's 2t to the 1. T to the 1 is just t, and so that would be a straight line. So a function, if you've got a equals 2t, it would just be a straight line. And the force function will look just like the acceleration function. So that sucker. It starts at 0, 2 when t equals 0. So there we are. All right, I also want to talk to you about something called boundary value problems, which you'll get pretty used to because once you take calculus next year, you'll spend the first 2 months going over something called limits. Like, what would this function be if the x was 0? What would the function be if x was infinity? What would the function be if x was minus infinity? So that's kind of limits. Boundary value problems are basically situations where you know what the function should be at extremes, and so you kind of make sure it works out in those extremes. This is something called terminal velocity. Terminal velocity, you know how we've been ignoring air resistance all this time because the math for it is terrible. Basically, your acceleration is proportional to your velocity, so you've got a constantly changing acceleration, and the rate of the change in acceleration is changing. So it's a mess until you learn something called differential equations, but it's really easy to figure out basically what the velocity will be at the extremes. So if we check this out, first of all, this thing is released from rest at time t equals 0. So your velocity is 0 at time t equals 0. And then we also want to know this whole terminal velocity thing. Anytime your air resistance force is proportional to the velocity, there will be a point where you're going fast enough that your air resistance force is equal and opposite to gravity, and your acceleration equals 0. And so you'll just keep floating to the ground at the same speed. That's what happens for people who jump into the airplane with a parachute. When they pull their cord, that changes their terminal velocity, so they're not going to be a bloody mess when they land on the ground. If their terminal velocity is slow enough, they will speed up until they hit that terminal velocity, and then they'll just coast all the way down at that constant velocity. And we can figure that out. They hit that velocity when this air resistance term is equal and opposite to the acceleration. I guess this is not a force. This is kind of like a air resistance acceleration. Anyway, our total acceleration will be 0 when we're at our final velocity. We're not speeding up, we're not slowing down. So if we make a equals 0 and solve for v here, it'll look like this. G equals bv if we move bv to the other side. And then we can just solve for our velocity when this acceleration is 0. And that's called the terminal velocity. So after a whole lot of time, that's how fast you're moving, and it'll be g over whatever this b constant is. So in this situation, we need to get it so our when t equals 0, the function is at 0 velocity, and when t is really, really big, it's going at the terminal velocity, and the biggest thing is infinity. So we're just going to say when t equals infinity. So we got our two situations. When t equals 0, v equals 0. When t equals infinity, v should equal g over b. So we are just going to check all these answers and see that which one is true, which one fits our boundary conditions, what it must be. This one we can just knock off right away because this is saying our initial velocity is not 0. So done, easy. It doesn't match with this guy. This one we can break off right away. It's when t equals 0, v equals 0 for this guy. If you set t to 0, it'll make the whole thing 0. But if you set t to infinity, the whole thing's going to go to infinity. It's just basically an infinity times and divided by some constants. So it's still infinity. This sucker, again, when t equals 0, v equals 0, so it fits this boundary, but it does not fit this. If you make t equals infinity, basically gt will be overwhelmed by minus bt squared. If you throw an infinity for t, infinity squared beats infinity, so it'll be minus infinity. For this guy, this doesn't work for either of them. Anything to the 0th power is 1. So at time t equals 0, v would be g over b in this case, because e to the bt or negative bt there doesn't really matter if t is 0. Anything to the 0th power is just 1, so you just have g over b. So it doesn't fit this guy. But this guy totally does work. When time t equals 0, anything to the power of 0 is 1. 1 minus 1 is 0. So you got 0 times g over b, which is just 0. So it fits this condition. And then if we try putting in t equals infinity, this becomes e to the minus infinity. Any positive constant greater than, or positive number greater than 1 to the negative infinite power goes to 0. Because basically what you're saying here is that this is e to the minus infinity. That's the same as 1 over e to the infinity, which is infinity. 1 over infinity is 0. As t approaches infinity, this term goes to 0. So you got 1 minus 0, which is just 1. And that times g over b. So it fits in both. This is the only guy. Anyway, that was a long one. Sorry about that. Then we have this guy. You could probably have figured it out yourself, but I thought it might throw you enough that it was worth mentioning. We want to find at what time the following times the force exerted by the elevator floor on a passenger, when is the force exerted by the elevator floor the least? So that's, we basically have a big minus small situation. Right here, when it's accelerating, normal force is bigger because he's accelerating up. He's getting faster and faster up. So in that case, it would be Fn minus, maybe I should write it over it. So right here we got, well, he's accelerating up, Fn minus Fg equals ma. So right here, we would have the biggest Fn. Right here would be the biggest. We've got the biggest acceleration. The bigger the acceleration, we got kind of like Fn, if we rearrange this, equals Fg plus ma. And so the bigger a is, the bigger Fn is. Right here, though, Fg is winning when they're slowing down, when they're accelerating downward because they're moving up and they want to slow down. So that's a downward acceleration. So you're letting gravity win in those points. So Fg minus Fn equals ma, in this case where you're accelerating down. So if you rearrange this, you've got kind of like Fg minus ma equals Fn. And so in this side, the bigger acceleration is, the smaller Fn is, and we're trying to minimize it. And so basically we want the biggest negative slope. The biggest negative slope here, when we're accelerating down the most, Fg is bigger than Fn by the most. So right here is where we got the steepest downward slope. And so this thing right here would be minimized, and so this guy would be minimized. So 6 seconds. This guy, don't even attempt it. You do not have the math for it yet. Next year, you'll get there, but it'll be more towards the end of the year. Right here, this one you can solve for it an easier way than I'm going to show you. I just want to show you the calculus way because we're learning that. Though you could totally do an average force sort of solution. Anyway, so we want to find the change in velocity, or the speed of the object, but it started at rest. So it'll be the same as the change in velocity. And we've got like a bunch of force and time information. So the first formula that made me think of, hopefully you remember this one. Remember, it's kind of like change in momentum equals change in momentum. And one formula for change in momentum or impulse is mass times change in velocity, and the other is F net times time. Both impulse, both change in momentum. However, we got this changing force with respect to time. So anytime you have a situation like that, instead of just doing F net times time, which is the easiest way to deal with it if you've got a constant force, you can integrate force with respect to time, and you will get change in momentum. So we can just do this way. So we just sub in our formula for force, how it relates to time, integrate it with respect to time. And if you remember, all we got to do is increase our exponent by 1. It was secretly 1 here. We increased it to 2, and then our coefficient becomes the old coefficient divided by the new exponent. So 0.5 divided by 2 is 0.25, which is the same as 1 over 4. You also have a plus the constant because keep in mind when you take a derivative of something, a rate of change function has no idea how shifted up or down it is. So we'd need to find the kind of like initial momentum, but we're told it was propelled from rest. So our initial momentum would be 0. Anyway, so at this point we just basically plug in our numbers. We know our mass is 5. We know we're interested in the velocity at 4 seconds. So basically we just plug in 4 for t, and then I move the 5 down. 5 times 4 is 20. So we got 4 squared over 20, 16 over 20, which is 0.8. And I'm sure the other questions aren't going to be easy either, but you should be able to do those using stuff you already know. Hopefully this was helpful. Thanks for listening. Keep up the great work.